Allegedly, we're on Twitch. Can anybody on there can check?
Is it on college Twitch?
Yeah.
Oh yeah, I see you. There you are.
And if you're lucky, you even hear yourself. All right, I gotta open up this stupid thing so I can answer people who are just like looking at stuff on their thing. Okay, great. All right. Thanks everyone. Please, somebody. Oh, there's 0 people on Twitch. Awesome. Okay, so hello everyone. In case you are super confused, I am the real Adam. Everything you heard last week was a lie. Let's see. Any questions from last week about the course? No? Everyone feel like they're ARM masters?
We're ARM.
Expert ARM people? No? Not yet? Do you want to be? What's so far, based on what you've done, what's the big difference between ARM and x86-64? Or ARM64, because there's several versions of ARM.
Loading registers sucks.
What was it? Say it again?
Loading registers suck.
Loading registers suck. What do you mean? You don't like loading registers?
I don't like loading the same register multiple times.
Ah, you don't like loading the same register multiple times. Interesting. Why? Is that a problem? Oh, with the big numbers and stuff?
With the big numbers.
Big numbers, yeah. Big numbers are a big problem, right? And I know Rob talked about that, right? You only have 32 bits for a single instruction, which fundamentally limits what literals you can put in there. It always helps to think of, for me, like how would I have designed this if I was designing like the ARM compiler, right? So you have 32 bits, you need to you have to deal with these limitations. Okay, so any other ARM comments, questions?
Actually, just on the side. So
yes.
like let's say we're doing x86 and if like the number is 128, then we'll have to do the same thing.
Ooh, say it again.
If the number is 128 bits, and the x86 register is only 64, so we'll have to do the same thing.
Yeah, so it gets tricky. I mean, I'll be honest, I'm not like a super ARM expert. I guess the big confession is I didn't actually have to read any ARM when I was doing XNU analysis because it's actually way easier. I had an x86 machine, and at the time you could run the same operating system versions on both, and it was way easier to debug that. Plus, as we'll see as we go into things, it's way easier to read source code and the decompilation code rather than having to dig into the binary code, but sometimes I would have to. But yeah, so if I remember correctly, the floating point registers on ARM are 128 bits, so they for sure have this problem. I think the other thing probably to think about is like a lot of, what you're doing is writing assembly code from the perspective of you're doing assembly code because there's shell coding and ARM or ROP and all that stuff, right? Like when you're doing exploitation, you often can control instructions and do those kinds of things. But if you are writing like an ELF file, right, you could actually you don't need to load immediates from instructions. You can always load them from memory. You have to probably then deal with, like compilers would have to deal with the performance trade-offs, right? So any big literal like that they want to shove into a floating point register maybe goes into BSS or something that they can then read from there and shove it into the register that way through memory. Yeah, exactly. But it's probably faster to use the immediates, but then you have to worry about, compilers always have to deal with, which is exactly what you see, right? Your instructions the size of your code gets larger when you have to do these things. Like if loading an immediate takes 5 instructions and you want to load 100 of them, your code is getting this 5x increase. So that actually may be slower because of caching and all this other stuff that has to happen, and you don't get the benefits of like, especially like in a tight optimization loop, you may not like the values and other things may not fit into L1 cache or the instruction cache because it's getting flushed because the instructions are so large. So this is why like when building compilers is very much an art rather than a science, because depending on one person's workload, it may be faster to do it one way, whereas another workload may be faster to do it a third way. So yeah, is there ambient music on the stream or just me hallucinating again? I don't know. I have no way of testing that. So hopefully it's a good hallucination, if that's what you're doing. Should clarify that's on Twitch. I'm not just hallucinating where that came from.
Sure.
Cool. Okay. Other things. I think the other thing that I don't really want to bring the slides, but another thing that Rob very graciously, is he here? I said he would be here today, so I was going to say what a great job he did, but since he's not here, I won't say that. But specifically, there was a discussion of why is ARM so weird. So a lot of you have been learning and dealing with x86. So do you feel that ARM is weird? Why? Besides the one we already talked about of 64 versus 32.
Well, for me, it's because there's no pushing the pop, so then functions programming methods are weird for me.
Yeah, there's no push or pop. That's weird. What other things are weird?
Plus, every instruction has to do bit strong, every so.
Yeah, but well, I mean, when you're coding, does the length of the instructions have anything when you're writing assembly?
Yeah.
Maybe, maybe not, but yeah, what other? Yeah, the stack has to be 16-bit aligned. That is so weird. I don't fully understand why. There must be some optimizations they can do because of that, but yeah, that's also weird. What other things? Do you guys remember how the conditional flags are set? Yeah, there's on x86, right? Every single add compare instruction will change the conditional flag registers. On ARM, you have to explain, if you want an add to change the conditional registers, you have to do the add S, which probably stands for set flags or something. So every like addition, multiplication, these operations have an S variant added to the end that updates the flags, which I guess can be nice because if you know you're already doing this, you can update the flags and maybe the processor has to do less work on every add instruction when it doesn't have to update these flags. So it gives more power. What other weird things? Like to me, that's weird because you're just used to these. You don't even think about the flags; they just get set. What are there? Any other weird things?
Using the linking register.
Using the linking register, yeah, it's super weird. Rather than pushing the stack, also for procedure calls, right? So the fact that registers are always passed into, or parameters are always passed into the register is kind of weird. And also weird that like the same first argument passed into the function is also the return thing, which I don't know, maybe there's some weird optimizations why that makes sense, but is there anything you like about ARM?
32-bit line, so it's faster for hardware to process the.
Yeah, cool. 32-bit line, what else? 4-byte instructions.
Loading multiple registers at the same time.
Loading multiple registers with the STP and LDP. Right, pairs of registers, yeah.
Disassembly is so much easier.
Disassembly is very easy because of this fact, right? You don't have this madness where you have to guess about how long the instruction sizes are, and then when you're doing the problem of identifying functions in a binary, it makes it way easier because you can just know exactly where the instructions are. Yeah, anything else? Nobody likes the super, like, I feel like this should like speak to your computer science souls that like the registers are just 0 through 31 and they start at 0 and there's no weird names that you have to remember of like A, B, C, D, but then RSI and all these other registers, RDI and the shit that doesn't make sense. Like, no, it's just you have X0 through X31 and these are your registers. Does anybody else like that? No.
Yeah, I was going to say the calling convention is really nice.
Yeah, the calling convention being in the defined in the architecture, I think is important, right? Because if you've done x86, you know that like the calling convention is different on on Linux versus Windows, and you can even in one project have different calling conventions, standard call, cdecl, all this stuff, and it just like makes interoperability really difficult. My guess is that's something that they learned from those architectures of how bad it is when you have different things. Does anybody miss fights between Intel and AT&T syntax? Yeah, there's no difference. It's just this is the way it is. You want to do it another way, just too bad. Any other good thoughts?
Like the super long instructions are pretty nice.
The super long instructions? You mean like having like 10 arguments?
Yeah, like you use one instruction that does like multiple operations.
Yeah, that's like bonkers. I hate that part, but it seems kind of ironic, right? Because you think like RISC reduced instruction set should mean that there's each thing does one simple thing, and then it should be, but then you can have really complex instructions. So why is it so weird? That was kind of the point I wanted to discuss.
not x86?
Because it's not x86. Yes, I mean, that's correct. But you could make, has anybody done Yon 85? Yon 85 is not, I guess it's weird in its own way. Actually, it's probably more similar to ARM, but anyways. So like, why is it weird?
Because we are not going to create x86, and that's why for us, ARM is moving, so that's why we're.
Ah, okay, familiarity. I would definitely buy that. That's cool. I think there's actually like a technical reason why this stuff is weird. Like, why is there an add and an add S? Or why is there a load register, right? LDR. You could do the prefix, postfix, and memory dereferences, and register. Like, you could do like 5 different things in like one instruction. Yeah.
This feels like ARM was made more to be created rather than written by like people.
Ah, interesting. I haven't thought about that, but that does make sense. I mean, if you think about it, right? Yeah, like assembly code should not be written by humans. Just like, I don't know, has anybody done web stuff? Do you like hand write HTML code all the time? Like, you can, but you can, you know, shunt that off to something else, or you use an ORM wrapper that talks to the database so you don't have to write SQL, right? This is kind of thinking at a low level thing that you don't need. Another thing is like, okay, so there's no push and pop. Why is there no push and pop in ARM?
Is it like expensive or something?
You know, you have the equivalent of a push and pop, right? That auto increments the stack pointer.
I just think that you don't have to use the stack. It's just like an allocated register. It's not 100% a stack pointer, but like a frame pointer.
Yeah, so you could think like it's more abstract, I would say, rather than push and pop that says dedicated register. You could technically use different registers to push and pop things too. Ah, great. Ooh, Twitch already got you guys. They're like 30 seconds behind this stream. So even though, well, I don't know if I want to say names on stream, but because this is well recorded, but yeah, this person's hallucinating music, but still is able to get there. It'd be a waste of 4 bytes, right? Every instruction is 4 bytes. So if you had a push instruction that does one thing, that takes up like from your, like if you think of like what are all the different instructions you can encode in 4 bytes, right? Your limit, you can have 2 to the 32 technically, but you fundamentally can't have that. So you can do things like with Yon 85 where you have the first byte, which is defines which instruction it is, right? So, but fundamentally, if you go that route, you are wasting all the rest of the bytes that don't specify that instruction because this push or this pop. So this is really, in my view, this is like the fundamental difference between x86 and ARM, because you don't want to have these special purpose instructions like push or pop that are just for this one operation, because you're wasting an entire possibility that you could jam stuff in. It's the same reason why you have add and add s, because you have an add instruction and everything else, but there's probably an extra bit there that they're like, what are we gonna do with this? Like, well, let's make it useful and expose it. Or like, the other thing that's crazy to me is like loading in constant values with left shifts a certain amount, right? That's just like efficient usage of the 32 bits that you have. So this is like it's like almost like a bin packing problem or something, right? That the instructors have, that the designers have to do of these RISC architectures. Yeah. So anyways, that's kind of, I think that's why it's interesting to think of these things as like the technical decision to be like, okay, we will have 4 byte instructions, almost forces you to be efficient with the instructions that you have and have each instruction be as flexible as the bits that remain allow it to be. So you'll just tack on all this weird junk to it. Cool. Okay. Any other questions or thoughts on that stuff? Okay, now, is the screen black? I can't see what's going on. Okay, perfect. Okay, so now it will be choose your own adventure. So I'm kind of still figuring out, as you maybe saw last week, I didn't even really know what the name of this class was. I only knew the AVR. Well, I did have it right on the syllabus, but so the big thing that I'm trying to do is figuring out how in the world to get you all access to a XMU system so that you can hack on it and stuff with minimizing costs and getting everything to run. So hopefully I'll have that in a week or two or so. So we're spending this time getting ready for that and doing learning ARM stuff. ARM 64. So today, and I think what I also want to do is make sure that you guys are getting some discussion and understanding of actual like applied vulnerability research, right? Finding stuff on real targets. So I have basically two different topics today that we're going to cover. One goal is ROP. So we're going to look at ARM and do ROP ARM and study that. And then I also have a discussion / lecture on target selection. So like how to go about even the first step before you want to try to find vulnerabilities in a real system. What system do you want to find vulnerabilities in? So I don't know how to let you decide, but I'll let you decide which one we want to do first. What was that? I can't hear.
Let's do a coin toss.
Oh, coin toss. Oh, that's cool. Anybody else have another idea? Yeah.
Yeah, let's do a coin toss.
That's the same idea. They just flipped each other out. Okay. Okay. Which one do we want as which? Heads will be ROP and tails will be target selection. Siri, flip a coin.
It's tails.
Oh no, this one says it's tails, but this one says it's heads, so we have to do it again. Okay. That's insane. Does anybody remember which one was which? Head ROP? Head ROP. Okay. Flip a coin. Heads. Okay. So we're doing ROP first. All right, cool. So you will, okay, so the next module is going to be ARM ROP. I should call it ARM 64 ROP to be more specific. Okay, the first assignment will be ARM ROP, or the next assignment, sorry, because we already have one assignment. This will launch at 8 p.m. tonight. I think that's kind of a decent cadence. It'll launch at 8 p.m. and then do the next week. We'll probably have 2-week assignments just depending on how long and how difficult the things take. For this in particular, so this is a little bit tough, and this is going to be something that hopefully will be easier going forward, but you have to understand that you are running right now on pwn.college on an x86-64 host, but you will have an ARM binary that you need to pop. That is the goal. So let's go in there. Okay, so there should be some stuff in here about how to do this. It actually is even more of a pain because your favorite tools like object dump, you can't even use correctly because object dump will say, I don't understand this file format because the one you have installed is the one with your architecture, so you have to install other packages. I should have installed everything in there, but like this is, I think, the first time we've done on pwn.college this like cross-architecture stuff, so I had to solve a lot of insane problems that I really am upset about that I can talk to you about later. It also means that debugging and using GDB is a two-step process. You can't just GDB and ARM binary and expect GDB to somehow figure out magically what's going on. So we'll go over that real quickly. So what we'll do is I'll start off with how to get started in this thing. And then we'll go to slides, talk about like how to even approach this, why it's different than x86. You should all have already experienced using ROP on x86-64, so that should be very familiar. This is the goal here is to then, and really the goal of this course is to try to abstract your knowledge away from just the one thing that you know, right? You know ROP on x86, but what is ROP, right? What does that fundamental thing mean? How do differences in the architecture take how differently you approach exploiting this stuff? And then we'll go back. I also found a CTF challenge. I was thinking it'd be fun to hack together for a while and break this binary. It's supposed to be a very simple ARM binary that we can go to because I don't want to spoil your fun by showing you how to do any of this stuff because I expect you to do that on your own. All right. And then let's see. Oh, this is a super giant class that I've like long in time-wise that I've never taught this long before. So I have absolutely no idea how this is going to go. What did we started at 4:30? Let's set a timer for a half hour. All right. That way we can take like
30 minutes. Counting down.
Like a bio break in a half hour. Okay. Cool. Okay. So this is hidden. You can't see this, so don't bother doing it. Also, it turns out it's a really bad idea when you tell like 20, 30, 100 students to all start a challenge at the same time. The dojo can't quite handle that yet. We're working on it. Actually, technically we should have a fix by Friday, is what I've been told. Practice mode doesn't work on this. I'm not sure exactly why. It's something that I'm going to complain to Connor about to fix. I can get into all the nitty-gritty, gory details, but okay. Do you all care about, like, I feel like you guys are experienced enough. I can use SSH and not have to worry about this stupid GUIs and stuff. Okay, cool. Cool. So I started my challenge. Wow. Okay. Okay, similar thing. Everything's in challenge. The binary will be in level whatever, level -1-0. The zeros have a little walkthrough, a little teaching, and the ones are slightly different. This run, can you all read that? You in the back? Read screen? Good. Okay. Yeah, this just executes the emulator and executes the challenge. So there shouldn't be anything there. I think I did this all correctly by clearing the environment and all this stuff, because there's weird QEMU variables you can set to get debugging, as we'll show you. So hopefully that's not there. But if you find a bypass, please let me know right away. The point is to have fun and do this stuff. Okay, so if we just run it, this should be very, I think this is very similar to the x86-64 ROP challenges. I will probably add, I think there's like 4 or 5 other challenges I will add that will be pretty cool and fun to show you some differences. One with like a statically linked binary with like thousands of gadgets that you have to figure out how to tweak your way through. And then one with a different compiler, because we'll talk about that in a second. So anyways, there's a win function. The win function address is here. We need to call that function. We need to overflow the saved return address. So again, this is, and we'll look at this in a second, but this is on the calling convention, right? So we have a BL call, which redirects control flow usually to the start of a function, and we'll store the return address in the register x30. And then when the program wants to, when the function is done, it calls a ret to return back to register x30. Okay. Stored here, 139 bytes. It means you need to at least 147, yada, yada, yada. I'm sure you all read this very in depth every single time and don't just do something like this. Okay, great. And it does the printing of the ROP gadgets. It's actually, as we'll talk about in a second, this is actually kind of not super helpful. It kind of can be helpful for your first one, but as you will find, your ROP payloads are very different on ARM rather than x86. So I crashed it, got a segmentation fault, awesome. If I pop this, I should get the flag and it should be good. Some tools. I have to go copy this because I do not recall this exact thing. All right. Object dump -D for disassemble. And then I can look at this whole big guy. And then I can get into the habit of reading ARM code, which is part of what you're learning here. So setting up the stack frame, subtracting B0 from the stack frame, storing x29 and x30. Why is it doing this store? And the link register. So again, another x86 difference, right? In what usually takes 2 or 3 instructions for x86-64 to do. This does it in 1. Does that really matter for performance? Yeah, maybe. I mean, it really depends. You have to get down into lower like micro-architectural things. If you learned MIPS and the MIPS pipeline, you would see like, well, yes, if you can do in 1 instruction what it takes 3 instructions to do, that 1 instruction will definitely be faster, because with 3 instructions, you have to have 3 things in the pipeline and worry if they invalidate things, and things can just go slower that way. The unfortunate truth is on modern hardware, all of this stuff, probably even on ARM, I actually don't know for a fact, but I'm positive they probably do something like this, gets compiled down to microcode that gets executed. So even what is 3 instructions or 1 instruction on x86-64 may get compiled down to like 10 instructions or 10 micro instructions that are doing stuff. And that actually enables the CPU to do things out of order and crazy things as long as what you see in the caches is all consistent based on the architecture. So this is why it's super hard to say like, look, 1 instruction versus 3 instructions. This is clearly better. It's like, that's not really the world we live in. And so you just have to run experiments, and then what you measured is true for that CPU, which may not abstract or be applied. Okay. Cool. Okay, so yeah, storing those things. Cool. Okay, so now we can look at stuff. I guess I did want to show you the workspace just because. Wait, what? Okay. Wait, how am I seeing this? Are you guys seeing this? Did I get logged out? Yeah, whatever. Okay. The other thing that's really annoying is there's only like 2 decompilers installed. Good old IDA. Anybody use IDA? Yeah. There's a problem with IDA. Anybody know what it is before I click OK?
Doesn't have 64-bit ARM.
It doesn't have any ARM. It's only the free version of IDA is only x86 and x86 64. So that sucks. I don't know what to tell you, but so anyways, it will not work on pwn.college on these challenges. You can actually, for a lot of these, you can use object dump. Apparently, Ghidra works. Anchor management does not. It hasn't been nixified. I definitely agree. Let's see, build nix. Anyways, that's the big problem. Is they needed to get the ability to. Like for this, I needed special libraries installed and special like the QEMU emulator and all that stuff. And so rather than going in and installing it so that it's on every single pwn.college challenge that ever gets launched, we now have the ability to define your own Docker container that I can say, these challenges need this Docker container, but you also want things like this interface and everything, and you don't want to have to, oh man, Connor's gonna, if he hears this, don't anyway tell him, because this is me regurgitating all the good stuff because this Nix thing is terrible, but it has a lot of great benefits where you can still get this X server and all this stuff in here, which I didn't have to install in my container. My container is literally just an Ubuntu 24.04 base installed the things I need, and you can do that here. Anyways, so eventually we'll get those other tools ready to go. New project. Oh God, I hate this project. Sorry, I'm just trying to be a good person to show you how to use this. Open. Import? Yep. This is why it's so difficult. Don't learn anything new. Just learn something and just get used to that forever. Use it for the rest of your life and never learn anything new. That's my advice. Challenge. Oh, I didn't. Okay. Has not been analyzed. Would you like to? No, I would just like to look at the binary. Of course, I want you to analyze it. Oh, come on. Hey, okay, here we are. Wait, why does this font look weird? Is this how it always looks? Is it really? Oh, God. I'm so sorry. Some people get used to this, and I don't understand why, but I respect people's ability to get, okay. I mean, I do kind of like them side by side, but I don't know, you just get so used to IDA. Anyways, so here you go. You get the disassembly on the right, the assembly on the left. No, I guess we can use anchor management. Is Zion? No, Zion's not here, but let's see. There should be a decompiler on the command line here. We'll just do all the functions. Oh, there's no way this is going to work. you think? Should we put bets? Is it going to work? Errors, always great to see.
That's how you know it's right.
Well, this is when you kill it because you realize this was a terrible idea and you go, Adam burning up the, hey, that actually worked. Okay, cool. So anyways, anger management doesn't work, but anger is installed and you can get some kind of, everyone knows C looks exactly like this, and this is valid C. But you can, let's see, can you even see the buffer here? So there should be a read. I'm just looking for a read. Yeah, read into V1. V1 is the address of V4. And V4 must be on the stack. And V4, maybe see it? Yeah. BP minus hex 93. So we actually do roughly know, like this actually gives us enough information about where this is on the stack in relation. So we should be able to pop this. Let's double check that I can't do in my head conversions between binary and hex yet. And then what did the challenge say? Did it say that it was 197? Oh, look at that. Hey, anger management got something right. Don't count on it though. Okay. Okay, so clear how to use it or start it. Okay, wait, I guess let me show you one more way. Just in case nobody's ever showed this to you. So I'm using SCP, secure copy, uses SSH. I'm gonna SCP challenge. And I press tab, which always takes a little time. There we go, level dot. So copy this file to here. What? Why did that work? Okay, anybody know the other trick? If you have SSH access, my friends, you can always get a file. This is a poor man's transferring of files. So what you're doing, if you've never done this or used this before, you SSH and the last argument can be a command that you execute on the SSH connection. So you SSH catting out the file, which will dump this to standard input of your terminal here, and then you can just redirect that to here. And I've definitely done this. You can also do this the other way. You can cat a file, pipe it to SSH, and then your command is cat dash, and then redirect that to a file. See, look, working around, like, why did SCP not work? I have no idea. Do I want to debug it? Absolutely not. Figure out a way to make it work, and it works. And if I really wanted to make sure, I would try to like MD5 both files to make sure they're exactly the same. I'm actually pretty confident. So the other thing you can do is use SCP or this SSH method and disassemble your buddy right here. Oh, so much faster. Okay. Yay, so there's main, welcome, challenge. I can look at challenge. V9, I bet that's our buffer. Let's look at the read, buff equals V9. Read into buff, and base pointer minus 98 hex. Wasn't that exactly what we looked at before? No.
93 hex.
Fuck, it's because of stupid reasons that I don't understand, but they do them. Oh no, yeah. Anyways, I don't know why it does that, but look at the binary. That's my tip for all this stuff in these offsets, because binaries don't lie. Okay. Any questions about how to access the stuff? Oh, debugging. Okay, great. Nope, that's not what I want. Okay. So the other thing is why is this not? Is this not installed? Screen? I actually prefer screen. Anyways, this is a problem I could fix, but I won't. I mean, I will fix it later, but not now. Okay. You need to, so first thing to do, so if you didn't, this is a grad class, so I kind of expect you all to poke around at stuff and not need to be handheld through all this stuff, but I want to show you how to think about approaching these things. So we know how the challenges run because we can see that it's running QEMU and then the challenge. So if we ever wanted to, and if Rob was here, he would tell us to pass -H and read the man page for QEMU or read the help documentation for QEMU. And there's a ton of arguments in here. The one that you can check out, the one we care about right now is debug. So just like, has anybody done debugging, like using QEMU system to like debug a kernel? I think you've implicitly done it in pwn.college without knowing it. If you've done the kernel modules, like VM debug actually creates QEMU and sets up a GDB server there to wait for your connection, and then you connect on another GDB instance. Similar thing here, this is all built in. So G1234, it's -G and then the port number, and then the port number. Okay, and then the binary challenge. And I would also recommend, it's a good, for what we're trying to do, it is a good idea to be used to things not working that should. So for instance, when I was doing vulnerability analysis on XNU, there's a whole setup you can go through to load, to get, I think it's KDB, kernel debug on the kernel. You can have it trigger a breakpoint, which then waits for a port just like this. It's actually a similar service, and connect to it. You can set breakpoints amazingly. Then you break on that and you try to single step, it just doesn't work. You can like inspect memory and look at things, it just doesn't work. I have absolutely no idea why. Do you think I want to spend weeks figuring out why I can't do this? No, you figure out other ways around it to debug what you want to debug, and just set breakpoints and look at things, and then continue worked. So that was fine. You can just set multiple breakpoints. You have to be very flexible in what your target allows you to do. Okay, so why isn't this doing anything? Yeah, it's waiting for something to connect to the port, right? You want to debug it, but it ran concurrently. You want it to wait for you to connect to it to actually start debugging. So we need GDB multi-arch. You will make that mistake of doing GDB and putting in the thing, and there'll be slightly subtle errors. You'll connect to this thing, and it says stuff about XML, which sounds like bonkers insane, but you just have to realize you did not use the right GDB because the stuff does work. So GDB multi-arch, I'm setting that up here. No debugging symbols. I don't have Jeff installed here, and there is like a weird thing with Jeff to talk to a remote target. I don't actually know if it works well or not. I don't know, but what you want is target, remote. I do localhost 1234. This is actually pretty cool if you think about it. Like what we're doing is connecting to a GDB server through a port. So this, conceptually what this allows you to do is debug a remote machine from your local GDB, which is really cool. I think it's really cool. So you technically could be running that GDB on your local machine, SSH into pwn.college, doing port forwarding, or doing local port forwarding through the remote one, and then connect your GDB to that remote instance and actually be able to do everything on your local GDB. The problem there is that connection can be slow, and like when you debug things, right, all the state of the CPU and registers that your GDB needs get sent back over UDP, and that can be slow. So if you can get on the same host, you want to, but in case you need to do this to debug two things, it's very useful. All right, great. Okay, target available, so I am here. Breakpoint, continue. And the other thing you need to be careful of is those register names, because you're used to x86 register names. You will type in RIP, you will type in all kinds of stuff that doesn't work. EBP, you will use it, get used to it, everything will be fine. Okay, and then here we can do everything we normally do in GDB, right? We can dump the stack, look at all kinds of stuff. Even though we're running the program inside of an emulator, so it's emulating, like QEMU is emulating all those ARM instructions and figuring out all the stuff, and then translating system calls and everything for you, so you don't have to think about it. Cool. So I can't digest win. So why can't I just jump to win if I knew how to find the address of win? Good point, maybe.
Are you talking about in GDB or in ARM?
In GDB.
GDB drops privileges.
Yes, well, yes, but exactly. So we ran the QEMU as our user. QEMU should not be set UID root, so it's not running as root, so we can get QEMU to do anything, and it will do it for us, but we can't get the flag, right? So you have to run challenge run. This is why you should not be able to debug the running instance that does get the flag. Great, okay, thanks. Some guy on the Twitch mentioned when you do the target remote, you can drop the local host here. I like including it, so you can completely remove that and just do :1234. That's the port you put into the -G command. I personally kind of like it because you are specifying exactly where to go, and it reminds you that you can go other places. But do what you want to do. Okay. Any other questions here? I think this gets you up to speed, and you can get going. Oh, great question. Does Home Tools work with ARM payloads on here? The question is, I do not know. I haven't tested that yet, but you will tell me soon. I think so. There's probably a package I need to install now that I think about it for that.
Like for creating ARM payloads?
Hmm.
It does.
Oh, it does. Yeah, it already did. Well, no, that was on the previous one. That's not this image, so it may not work on this image.
I think Home Tools installs all the cross BS stuff.
I don't know.
Only for assembly do you actually need something not just it, right?
Yes. Yeah, it actually should be fine. I don't know. I'm just thinking of if you ever need it, maybe you're doing some ROP payload that does mprotect or something, and then you want to execute your own shell code, basically. Like making sure that pwn.tools pwn.assemble actually does work with ARM64. It should, but I haven't tested it, is just what I'm saying. So tell me if it breaks.
I think if you have a payload package, it should work.
Yeah, but does it work here? Yeah, you need that special bin utils thing, which I don't know what it does. Okay, any other questions here?
You can use tools to SSH tunnel and just
Oh, great question. No, we're gonna get there. Twitch user. Maybe a stupid question, but isn't the return address in a register? How can we overflow? Great question. Say it again.
Because when you're in challenge, whatever it is, it pushes a value of the register, which is the thing that you overflow. And then the main returns it will use that value.
Yeah, let's look at the first instructions here. So if we look at the challenge function here, the very first thing that happens is the stack pointer, it subtracts hex B0 from the stack pointer, puts it into the stack pointer. Also, isn't this crazy? Now you don't have implicit destination registers. You actually are very explicit of where the thing goes. I actually really like that. It's cool. And then this one here, store pointer, STP, is going to, let's see. I always have to remember how this is done. I think this will store it at SP plus 160. So it'll take X29, put it at 160, and then put X30 at 160 plus 8 and store those registers in there.
I think it does the function first and then it adds. It's post-fix, right? So it does the function and then it adds.
Yes. Okay. That also makes sense. We can look at the documentation later, and we'll do that in a second. But anyways, the point is, it's stored on the stack somewhere, right? And why does it need to store the return address on the stack if the return address is passed into a register?
Because something might be there in the external study.
Something might be what?
Something might be there in those registers. Because in external study, the address of main is there, right? So main must have been called by some other function.
Yeah, but we just got called. We don't care about main. Somebody called us, but they put in that register X30 of where to go. So why do we need to store it onto the stack?
Calling preserved.
What was it?
Calling preserved registers.
More specific. Feels just like a word salad that you just said.
No, there's caller saved and calling saved.
Yeah, but when do you need to do that? Does every function need to store the X30 onto the stack?
So you have like a
Yeah, what's a leaf function?
If I remember correctly, they are like the last function and the call trace.
And why is that important for this discussion?
So if they're a last function, I think they don't need to store the register on the stack.
Why?
They're not gonna get. It's not gonna get overwritten.
Exactly. They're never going to get called, which means that it's totally fine. Like you're not calling any other functions. So if your function ever needs to call another function, you need to store x30 on the stack because it's a call. I mean, it seems silly calling it a caller preserved register because of course it's the return address, and when you call a BL, you need to come back. And so, but yeah, that's another one you think about why, right? Because I always like to think of like, oh, that's interesting. It's different from x86. Why? Right? I think it's because you can see that you can make tail or leaf functions more efficient, right? Rather than every single time you have a call instruction, it shoves the address onto the stack. When in leaf functions, you don't need to do that. So you're saving space there. Very similar. Anybody remember the red zone in x86-64? Well, that's the question. Yes, you're asking me. Have you ever seen a function that writes past the stack pointer? Right, so on, I believe it's like, I can't remember if it's like 128 bits or something like that, or bytes. No, it can't be bits. It must be bytes. But anyways, it's implicit stack space. So when your function is executing, there is an implicit space that is saved that will not be I think it's like even if there's an interrupt or anything happens, like it's guaranteed that nobody will write to lower than I think it's 128 bytes of the stack. ARM has the exact same thing, and the reason is so that you have these optimizations. Like a leaf function doesn't need to set up its own stack frame if it uses less than 128 bytes in its local function. It doesn't need to do the decrementing stack, and then in ARM it doesn't need to do the saving of the x30 register. So it's making these things more efficient, and these special cases of these tail functions become way more efficient. Cool. What the hell are we talking about? Oh, yes. Okay. Yes. So there would probably then be, if you have an overflow in a function that's a leaf function, there's nothing to overwrite. There's no saved return address on the stack. That return address is in a register. You are just like SOL. Well, of course, you could maybe have, actually, that would be a fun challenge, but you could probably, depending on if the frame pointer needs to be saved or is saved, then you could control the frame pointer. Otherwise, you can control whatever is stored in the function that calls you, right? Cool. Okay. Yes, so this was all of the how can we overflow, which is exactly what we're talking about here. Because this STP exactly right here stores the frame pointer and the link register onto the stack. And then if we go to the end of challenge, and we'll know it's the end because we'll see a ret. Is this really a ret? Actually, I haven't looked it up. I usually try to not say things I don't actually know, but I'd probably put money on. We talked about like pushes and pulls, right? Pushes and pops, right? So this seems wasteful because it's one instruction. I believe this is just syntactic sugar for branch register x30, but it's just nicer, much nicer to see the ret because everyone is familiar with that. But this way, you don't have one instruction. You have what looks to be one instruction to you, but actually maps to a more complex function that can branch to any of the 30 registers. Okay, cool. So let's go through the prologue here. So here, load pointer. So loading x29 and x30 from the stack pointer plus 160. Yeah, is this infix? I think this is not infix. I think this doesn't change the value. I think it changes it when it's outside. Like another example somewhere. Yeah, because this is, so basically wherever the stack currently is, whatever stack pointer plus 160 is, take that memory location, put it into x29, and then at stack pointer plus 168, move that into x30, and then increment the stack pointer by B0, filling up this stack frame. I actually really hate how it like doesn't do everything in hex. This is like driving me crazy. I don't know if that's also for you all, but I don't know if somebody finds a way to make GDB and all these tools do that, that would be amazing, because and all the instructions, I just want to see hex. Okay. So the stack frame. Cool. Okay. This is, yeah. So this is exactly what I wanted to talk about here, right? Is that there's fundamental differences here between x86-64, right? The fact that the return address is passed in a register is important. Also, the way parameters are passed, right? By passing parameters through registers and all parameters. I guess it's very less similar to x32, where everything was passed onto the stack. But yeah, so even having stack control, so setting up if you're trying to call a function and pass it arguments, you need to use gadgets in order to put things on the stack or from places you control into those registers before you call that function. Okay, and we talked about that. Yeah, so this is exactly what I wanted to show, is that also the other thing that's crazy is that different compilers are different. This was not something I was prepared for before looking at this. So, and maybe anyways, you'll find it in one of the challenges that I will release later, but I will compile these with a different compiler, and you will see that like even the exact same source code, the overflow that you have to do is actually different because the compiler does weird things with how things are laid out. So important things to remember of all of these, right, is, okay, where's my buffer on this stack? How many bytes do I need to overwrite to get to the saved frame pointer, x29? And then the next 8 bytes will be the saved instruction point, program counter, and x30, and then that's where we want to go. I guess saved link register. It feels really weird calling it that. And because we're trying to do exactly this part here. Okay, great. Yeah, so this is, there's one important thing. So, okay, wait, this thing. Okay, we're almost done here with this part. So let's do, so one of the most classic ROP. So for instance, we want to jump to this win function, right? That's our goal. Everyone agree here? And when are other times? So oftentimes we will not have just a win function. But why would we want to jump to a whole function? Say it again? Alignment? Yeah, maybe. I think we technically jump to any instruction as long as, I think instructions are fine because they're 4 bytes. I don't know if we can jump to halfway through an instruction. I think that will cause a sec fault, I believe, or any other non-4 offset into an instruction. In any of your exploiting careers of targets, have you ever had to jump to a function or something? What was it? Exec VE? Yeah, so jumping to ret to sys, ret to libc, right? That's what it's called. That's too many rets. But yeah, that whole idea of just like returning to a specific function in the library that does what you want to do, that's like great because you're reusing a whole chunk of thing rather than building it up through little gadgets, right? What other things?
Sometimes your overflow isn't enough to do anything super meaningful, so you need to reread and re-overflow some more. Yeah, so it is if you're, you may not have enough of a payload to generate a great ROP chain, but if you can redirect control flow back to main and get another write and maybe get several of them, you can build up a nice ROP chain. Yeah, that's a great example. Yeah, so executing system calls, returning into libc, all that stuff's super important. So let's go. I'm confident that you guys can all give input to this application in order to overwrite the saved link register x30 and then redirect control flow. So let's put ourselves in that mindset. We have just, because I think it's really important, one of the things that I always emphasize is like, you want to be able to kind of,
let's say, do this stuff in your head. It doesn't have to be completely in your head. I think it's totally fine to draw and do that. I do that all the time when I'm looking at things of like exact offsets. But being able to look at these instructions and walk through step by step exactly what's happening so that you can be prepared for when you actually are running it against the real target is super important. And so, for instance, let's say we're here. We've probably done the overflow. We've changed here now. X30 is, where do we want to go? The win function. We want to win. So we want to go to the win function. We put it into X30. Now this instruction executes. Our stack pointer gets incremented, cleaning up that whole thing. And we have the ret, which is a branch to register X30. That takes us to win. All right. What's the first thing that happens at win? So it stores X29, whatever was in there. We controlled that because we must have controlled that because we, and actually that's another important thing when you're talking about overflows, right? It's like, what did you overwrite and change? Because X29, if there had to be something special in there. But, so we're storing X29 and X30, and this is a cool way that you can see that like we're doing a ton of stack setup just in one instruction, right? Or function frame setup. We are storing this X29 and X30. So this is, I believe, the prefix operator. So this will do stack pointer minus 16 and then store at stack pointer at that current stack pointer, which is stack pointer minus 16. It'll store X29 and then 8 bytes above that will store at stack pointer minus 8. We'll store the, so this was basically, you can think of this as exactly equivalent to like push X29, no, I guess push X30 and then push X29. I have to diagram that out. But anyways, the semantics are X29 goes at stack pointer minus 16, and then 8 bytes above that at stack pointer plus 8 is where X30 goes. Okay, but now the stack pointer is pointing right to X29 and X30, right? Everyone agree? Okay. The next instruction, what's the point of this instruction? Why? It's moving the stack pointer into the X29, which is the frame pointer. What was that?
Is it a leaf function?
Is it a leaf function? No, because we're doing a lot of BLs here. This is great. If I don't get good answers for you all, I can just go to the chat. It's like having a better, smarter kid you can go to.
Yeah, it's just moving the base pointer down to where the stack pointer is ready for it.
Yes, so setting up the new function frame by setting up, so now this current function frame starts at where the current stack pointer is. Exactly. Cool, okay, and I think actually your comment may actually be mostly, it's not a leaf function because it's calling things, but I think there's no local variables here, so it's not decrementing the stack pointer anymore to set up actual space on the function frame. And I believe, I don't know this 100%, but I believe so that you can debug and walk the stack back up, every function pointer should point exactly where the other's function frame is. So at your current X29, if you dereference that memory location, that should be your caller's X29, and then all the way back up your call stack, and that allows you to walk that. And then you can know exactly where you came from, because at 29 plus 8 is the stored link register. So that's how you can walk the whole stack back up. Okay, do we care what else happens here for our exploitation purposes? Not really, stuff happens, right? This is all stuff that's like gonna happen in this function, it's target specific, whatever, blah, 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 blah. Okay, now we get to the good stuff at the end here. Now, what happens here? So this is a postfix operator. So this is, yeah. So when it's, I guess the way to remember it is when it's inside like this and there's a exclamation point, it does the operation first. If it's outside of it, it does this operation, because this makes sense of loading LDP X29 X30 SP in brackets like this means dereference SP, load whatever the 8 bytes that are there into X29 and the 8 bytes above that into X30, and then add 16 to it. Okay, so we loaded that. Now what happens? When we do this ret, what happens next? What was that? X30. X29 is the frame pointer.
Yeah, and the stack where the frame goes back to X29.
Yeah, but what's in X30? What was it?
Win.
Why is it win?
Because we already set the X30 as win that exploitation part.
Yeah, so we went right to win. So this will, when we return, go back here. And then what'll happen when win returns? Yeah, it'll keep doing this forever. I think in this, I think in this case, you'll run out of file descriptors. You will open up every possible file descriptor for the flag. The flag will print out, and it will just keep printing this over and over and over and over and over again. The reason why I'm telling you this now instead of letting you figure this out on your own is that I want you to be nice to our servers, and I don't want them to just do busy work for no stupid reason. So if you can protect that. So this is the pitfall of returning to the start of a function. And this is exactly because of the architecture saying that jumping to like a function uses whatever's in that register. Well, how did you get there on a return? Because whatever is in there is in that register. Yeah, that's a great question. I'm going to ask you. I'm not full of answers. You're full of answers. What was it?
Skip the first instruction.
Skip the first instruction. So what happens if we jump here? Yeah, and then, so if we skipped and jumped to win +4, move stack pointer into X29, and then do all the stuff, and then finally at the end, where was I, win? Yeah, so then go load from stack pointer +16, oh sorry, from the stack pointer, load into X29 and then X30. So those were on the stack right above where the stack pointer is. The stack pointer is actually getting, because it's here in this case, it'll get popped off 16 bytes every time. So yeah, then we don't have to deal, if the prolog, this is the beauty of ROP, right? Rather than having to go right to the start of a function, go to another point in the function, and then you can generalize that concept and go, well, let's just skip that part where it stores it on the stack. This means that your payloads will be very different than what you are used to in x86, 64. This is part of why I think this is fun to do, because you have to get all of these offsets of calling these functions correctly, and they're going to do different things, and it's going to be fun. Cool. Any other questions?
We know that the for ARM, the stack pointer needs to be 16 by 9, right?
Say it again?
The stack pointer needs to be 16 by 9 for ARM.
Yes, the stack pointer always has to be 16 byte aligned.
Right. So in the prologue of the challenge function with prologue, I can't see like the stack pointer needs to be 16 by 9. So.
Yeah, so the way I would probably, I don't know the direct answer to your question. My intuition is that every single one of these instructions has to leave the stack aligned correctly.
Okay, so if that's the case, then only STP and LTP should work, right?
But even then, like if ever that instruction was executed, the stack must be aligned properly. Like especially if you're executing an entire function, right? An entire function must, every single instruction has to leave the stack aligned correctly. So I think you don't need to worry about that.
So how do I reduce it? Keep the stack aligned if I do a single slew for a
yeah, so that's on gadgets. You would need to worry about that more. Yeah, and if you're using a pushy pop style gadget, you will need to do that. Oh, let's look if did I install this? Why does nothing work? Okay. Okay, well, it's gonna be hard to find any gadgets without any tools, but we'll get that fixed. There should be something here. Anyways, okay.
You can use ROP gadgets for 3 yard cap.
Oh, of this thing? Ah, there we go, okay. I believe this has, yeah, okay, great. It has support already for ARM. If there's other stuff that's not installed, let me know. I think I use Ropper usually, but or other stuff. But anyways, so yeah, tons of weird gadgets. So you will have a fun time with this. But that's the goal. Okay. Anything else? Okay, let's break for 5 minutes because I've been going for over an hour. Okay, I guess I'll pause the stream. Now you can listen to music, Twitch stream. Or do I just stop streaming? I don't want to stop streaming. I'm just gonna mute it. Okay, hello Twitch. Hope you enjoyed that break. I hope this stuff works. We'll see. I actually have no idea if it's gonna work, but anyways, it won't break right now. I'll just fix it later. Okay, so we did that. Let's do, because I don't know how long the CTF, the live breaking will work. So let's shift gears and go over to how to identify targets. Okay, wait, I want to check, make sure here. Yeah, whatever, they can see the presenter mode. Okay, cool. So why do we care about picking targets? You might pick something where, let's say the developers don't want you to find bugs in their stuff or vulnerabilities in their stuff. Yeah, that's definitely true. What else? Follow me. Okay, good. What else?
Some targets are easier than others.
Some targets are easier than others, but why do you care about either of those things?
You want to find bugs.
You want to find bugs? Finding bugs is easy. Look at your own code. You will find bugs.
Picking targets that are more exploitable.
Picking targets that are maybe more exploitable than others? Yeah, so what I want you to be thinking about, and I guess Jan talked about it a little bit, but so the background here is I spent a year doing basically vulnerability analysis, targeting the XNU kernel and Mac. I didn't originally intend to target the kernel. I wanted to do like Apple stuff, and so I read a bunch of books about it and looked at user space programs and tried to, I think I was not decompiling, but disassembling the kernel cache, which we'll get into, but is basically like the kernel and every single driver in it. And I set that up, and it took literally like a day and a half in IDA to disassemble. Anybody know, or sorry, not just, yeah, to even disassemble and create the control flow graph and everything. Does anybody know the trick, or I think it used to be an older trick to speed up IDA if it's taking a long time? Close like the console window and all the other windows, because there's GUI refreshing that happens on like those side panels and stuff, and it speeds it up by like 30%. It's like crazy stuff. Anyways, so I spent a lot of time, and what I'm trying to get through here is the lessons that I learned. So for those that don't know and aren't in academia, so sabbatical is a specific thing in academia where every 7 years, so your 7th year, that's where 7 comes from. Sabbath is similar to sabbatical. It has the same root. Every 7 years, you can take time off to go in different research directions or whatever, and that's like negotiated through your contract. It's part of the reason why us academics put up with these lovely students and our lack of pay compared to our industry peers, because we get a lot of freedoms. And one of those freedoms is the ability to just like not have any university responsibilities for a year and be able to focus on other things. So I focused on bug finding and vulnerability analysis. And as part of that, some people, when they do a sabbatical, go and work at a company and make a bunch of money. And that's a great way to see what research problems like companies have. And you get to make a salary because even though, you know, your lovely tax dollars are paying my salary at ASU, well, if you guys are working, I don't know if any of you are working, but the broader you. And so the university will let you have that time off, but you, depending on your university, you don't get full pay during that full time. So my plan was I would make up my salary by finding bugs and reporting bugs. That was the idea. So this is something that I actually had to learn the hard way about, not just like what to target and why, but I think I learned a lot about like approaching it from the mindset of maximizing your money payout, which I did not think of as I was starting this. I really only figured that out the last like 3 months, and then couldn't do anything with that information. So this is why thinking about, because I spent months just poking around app like Mac OS, learning different things, but like not really, probably took like 3 months until I really like focused on the kernel and was like, okay, I'm going to find this thing. But so I want to talk about, and I want us to discuss how to like pick targets. So one thing you can do is just randomly, right? Just like point at a thing There's a GitHub project. I'm going to look for bugs and vulnerabilities in that target. Probably not effective, right? Because just like random stuff may or may not. You will find bugs by doing this. I absolutely guarantee you. If anybody, a good habit to do for bug finding is like reading code. You can just read random source code. If you do a Google, not a Google search, a GitHub code search for just system, and start looking at every C code that has system, you will absolutely find a vulnerability. Or probably in Python, os.system, you will absolutely find stuff. There is stuff out there. You could, if you wanted to find real bugs in real systems, you could do this for sure. You can choose what you know, right? What's the benefit of choosing software that you know? What was it?
You already know some of the code.
Yeah, you already know, well, maybe the code. I mean, it depends on how really familiar you are with it, right? But it may be something you're very familiar with, so you know how it works, right? That's a key thing of any kind of vulnerability analysis, is trying to identify and understand the target at a really deep level, so they can understand what are bad things. What's the downside of choosing what you know?
The sample space gets a bit too small.
Say it again.
The sample space becomes a bit too small.
The search space becomes too small. Yeah. If your daily driver is some Nix OS, like if you find some Nix bug, I'm sure people will care, but like, would you want to find a bug in that or a bug in, I don't know, Exchange server? Anybody know what Exchange server is? Anybody? What's Exchange?
Email server.
Yeah, email server. That's almost every large organization on Earth uses Exchange server to run their email. If they're either on Google or this, basically. And Exchange servers, do they have, like an email server, does it have to be exposed to the internet? Yeah, it has to. It collects messages. You find a bug where you can send an email to somebody's Exchange server and pop their Exchange thing, you've taken over like multi-million-dollar companies' emails. That's like insane. So this is part of some things to think about. Also, what's available? What do you actually have access to, right? I mentioned Exchange, but anybody here have experience with Windows Server? Yeah? Do you have access to Exchange? Yeah, you have to have an MSDN subscription in order to like install Exchange. I think back in my day, students had access to MSDN and it was great, but you need access to the software, right? Like it would be super cool to find bugs in industrial control systems that do nuclear enrichment and all kinds of stuff, but like, I don't know, do you have access to that stuff? If you do, don't say anything to me. I don't want to know about it, but this is the kind of thing, like what's available to you. You do have to think about this stuff, because you can set your eyes on a target and then be like, okay, well, crap, how do I get that? How do I run it? And we'll talk about other things. Now, these are kind of, one of the things, I mean, what it really comes down to, honestly, is you and your time, right? If you're going to invest time in finding bugs, like you should be thinking about, and I'll get there in a second, like what do you want out of this? Right? And if you want to have an impact and you want to find bugs that are important that people care about, anybody know of a named bug off the top of their head, like a bug that has a name? Heartbleed? What are some other ones? What was it? Log4j. That was literally, does anybody know Log4j? Yeah, was anybody looking at bugs in Java logging libraries that allowed arbitrary command execution that every company on Earth freaked out about, because every Java software uses logging, and so many companies use Java behind the scenes in their web services? Yeah, any other bugs, named bugs? Spectre, Meltdown? Yeah. Huh? Shell Shock? Yeah, that was a great one. Yeah, so it's not that you necessarily, I wouldn't, the question is, will we go over extracting firmware from real devices and how to emulate it for VR purposes? Absolutely not. That's something that you can do on your own. The ZenBleed or the XZ backdoor was a great one. And so it's important to consider, like, something to think about. You have limited time. Where are you going to spend your time? Is it on something important? I'm not saying you should find bugs, and I'm not even saying that I like these weird named bug things. I think it's kind of a weird trend, but I don't know. I understand why people do it. But, that's like, do you want to spend your weekends or your life finding bugs in Game Boy emulators? I don't know. Like, it's cool, but, availability, like we talked about, right? Can I get my hands on that thing? Can I run that thing? This is honestly, I will try to abstract this as much as possible, but this is the main thing that's a pain of doing XNU research. Because, like, especially with the ARM and the Apple Silicon Macs, they have locked down access to these systems so much that, like, loading, because on the Intel Macs, you can load alternative kernels and stuff. So loading a KSAN kernel, which has address sanitizers to prove that you found some out of bounds write, because you can get a KSAN report that you can use in your bug report to Apple, is super important. But, like, I had to use separate machines. Like, I had kept an old laptop around for that. Like, people buy other machines for this, and it's a pain. Yes, chat is very good. Weird names are at least more recognizable than CVE numbers. Absolutely agree, which is why that's, I think, cool. Money, right? If you're going to be spending your time, there's oh wow, I should have had a whole slide on ethics. We should probably just talk about that next. Yeah, well, maybe, I mean, I like learning stuff, but when I say money, I mean, this was like literally my reality, where I had to, like, hypothetically feed myself by the bugs that I found. And so that can affect what targets you choose. Does the Game Boy emulator have a bug bounty program? I mean, maybe. I don't know. I don't write Game Boy emulators, but they probably don't. Yeah, exactly. And what is that bug bounty program like? How often are people paid? What do you know about that? Do you know anybody that's getting paid by that? The other thing, this isn't a word, but I think maybe you probably know this, how it's kind of similar to availability. How easy is it to debug this thing? Is it such a pain that it makes you want to rip your hair out? On one hand, that can actually be a benefit because it's a bit of a moat, right? If you think, like, nobody else is probably popping that target because it's such a pain to debug and figure out what's going on. But if it takes you a month to go from, I know this bug exists, to creating an exploit or doing something that you can demonstrate to the bug bounty program or whatever you're doing, then that's a lot of time that you're not finding other bugs, right? You're maybe learning a lot, which is great. I guess I should have thought of, like, learning stuff. Great. The question on here, how do companies like Raytheon or other defense contractor companies decide on targets? Yeah, they do not decide targets. So there are, let's talk about, I'm just going to make a slide so I can fill it in later. See, JIT is not just for compilers. Okay. So, ethics, don't go to jail. This is what I always tell the 365 students. I'm actually not worried about any of the 365 students going to jail. They learn not quite enough to even be dangerous, and the ones that do know how to do things are usually smart enough where they're not going to go to jail. And for here, specifically, we're talking about vulnerability research. This is like finding bugs in software, right? You need to be able to have it. You need to be able to run it on your own machine. Never do this on a production real system. That's just, like, absolutely crazy unless it's part of the parameters of the bug bounty program. Facebook is very good about this. They have a completely separate social network and testing system that you can do everything on there. And as long as you use that, you can test their, like, basically test production system. And then, so the question is, then what happens when you find something? So you find a bug, it's an exploitable bug, you've written either a proof of concept. I guess, what's the difference between a proof of concept and an exploit? Yeah, a little bit tricky. I wouldn't necessarily say that a proof of concept shows that it's exploitable. It shows that the bug exists and that it's probably a real bug. Whether it's exploitable depends on your goals, and it may be it's one of these things like it could be exploitable chained with other things, right? Or there's a lot of mitigations in place, but like, yeah, so, but taking that step from like, this is a proof of concept, something that triggers a bug that a developer can use to identify that bug and fix it, to a full exploit chain that actually achieves control, is there's a ton of like variance in there and difference. We'll try to learn as much as we can, because I think that's interesting, of like how systems work, of how to build like an exploit chain and these kinds of things. That's also what I want to find and not just find things, but exploit things. That's the fun thing. Okay, so then, so what are your options? So you found a bug, you want to get paid. What are some things that you guys have heard of to get paid? Yeah, you make a proof of concept. Let's say you have that. You have that in your hand. Yeah, so there's different types of bug bounty programs. There can be, there's like, you can think of like outsource bug bounty programs where the company itself doesn't run it, but another one like HackerOne or one of these other sites has a bug bounty program. And it could be an in-house bug bounty program that is run by the company. I believe, I don't know for certain, but I think Microsoft was one of the first companies to do a bug bounty program. And so companies do this. So you find the bug, you report the information to the company. I don't know, what happens next? They fix it, hopefully, right? So you can, so yeah, they will almost always attempt to fix it. This is like a whole thing of like, how much time do you give them to fix it? And if they're dragging their feet, the theory there is like, you're not that smart, so if you found it, somebody else better and smarter than you has already found it and maybe actually weaponizing it and using it against people, so it's better than everyone knows it's a problem. Yeah, it's a whole thing. I don't want to get into all this of like bug bounty. We can talk about that later, I think. But basically, so like you can report to the company and it gets, it's highly likely that it gets fixed. And they will often, depending on their bug bounty program, give you some money. Now, the next, let's say on the ethics spectrum, this is my opinion I will be telling you. I hope you think that is reasonable, but whatever, you're your own people. I'm not going to control how you think. So kind of the next step over is companies like, who does Ponta own? ZDI, yeah, ZDI. So why does ZDI pay for bugs? Does anybody know? Wait, let me go over here. Why? You've been to Ponta Own and done this. You've gotten money from this company. You don't know why they give you money? Okay, if anybody gives you money, you should know why. This is a general life thing. This is literally why we're talking about ethics here.
Because don't they actually partner with the actual vendor to pay out this money?
That part I don't know. I think, yeah, partly, but a lot of those targets don't necessarily work with them. And you can do it outside of Ponta Own and sell bugs to them. Do you know, Mitch?
Yeah, I asked them about this a lot because I didn't really get it, because they don't actually partner with most of the people they like ask for bugs for. They kind of just like put out bounties and then just report them themselves afterwards. But I think it's mainly a marketing thing for them. They get to go.
A marketing where?
What do you mean?
So they specifically, at least the way they were created, they were with an antivirus company. So they would take the exploits that they would buy, they would write signatures that they could push out to their AV system and say that they have basically pre-0-day detection of these bugs. And then they would work with, probably concurrently, then report the bugs and work with them too.
Right, yeah, it's Trend Micro, ZDI.
Exactly.
Yeah, they put it in their product, but they also, I think mainly what the guys are saying is they just get to put the numbers in their presentations, like we found, or we, facilitated the fixing of 30 critical insane 0 days and gave out millions of dollars. They're the largest competition in the world. So yeah, I think it's be a marketing thing, and they still get money from bounties. Like if they turn a Chrome bug, they still get a bounty. So
interesting, but the money they give you is more than the Chrome bug.
Oh
so
yeah, it's like double.
Exactly, yeah.
Whatever
So
bug bounty for
they're making money. Somebody's getting paid some way, right, through this
Yeah.
stuff. So it's important to remember. So that's also, as you notice in the spectrum we will walk down, the money that you can get paid for this. I think the good, the thing I like to go with is like, I think the point, actually maybe have I increased it, but anyways, when I was doing this stuff, a fully remote exploit for the iPhone, that's 0-click, meaning absolutely no interaction. So you send a text message or something to the user's device, and it completely takes over the device all the way to the kernel. So complete root level, well, no, actually we'll get into this. On Mac, the root is not the final word. It's actually kernel access because of all the system integrity protection and stuff that's on there. But that's $1 million. So Apple themselves will give you $1 million for that. I actually don't know if anybody's done this yet. I don't know. Because that's like, that chains like, I don't know, so many bugs together. It's like, it's hard to even think about. And if you send that to somebody like ZDI, they will give you much more than that. I don't know exactly how much more. You can see all of this. Then you get into, let's say, and I'm not trying to offend anyone, there's different steps. So then, like, okay, we are in the United States right now, at least everyone in this room. You could sell that information to a government, let's say that you trust, like the US government has I think it's VRP is what they call it, a vulnerability research program or something like that, a reporting program, where you can sell this vulnerability to the US government. They actually have a system in place to decide if they should disclose it to the vendor and get it fixed, or if they use it operationally and never disclose it to the vendor. So that's up to you and your personal ethics, whether you're okay with your stuff being used by the US government. Then there are further, and that, I actually don't know exactly how much that pays. I haven't actually done any, I stuck just to the reporting to Apple, just to be very clear. And so then the next step beyond that is basically, well, I guess there's 2 more-ish steps. The next one would be reporting it to a company that will pay you a ton of money and will never tell you who they're selling it to or where it's being used for. So you have absolutely no control over what governments or things that are buying that, and you are getting paid to keep silent about the stuff that you found. And then the even one beyond that is like dealing directly with what I would probably, and some of you would probably consider, a hostile foreign government that buys this stuff to use against their citizens or journalists or all this kind of stuff. So anyways, it's very important to understand like what you are doing and where, in what context it could be used, so that you are comfortable. For instance, if you just think, I'm a cool hacker, I like finding stuff, I love CTFs, I love like this like an actual real world CTF, I've got this exploit against the iPhone, this is awesome, I don't want Apple's $1 million, I want like $10 million or 15 million or whatever the price on the street is for a 0-click remote iPhone exploit. And then you find out that Google Project Zero does a teardown of your exploit where they caught it being used against, I don't know, a vulnerable population in China, for instance. I don't know, you have to like live with that the rest of your life. So think about the decisions that you're making, make great decisions. And then the whole reason why we got onto this, somebody asked about defense contractors. So one of the jobs you can get for doing vulnerability research, especially in the United States, if you can get a clearance, is with a company that does vulnerability research and finding bugs. There, you do not define the target. The US government defines the target and tells you, find us bugs in here and find us exploits and vulnerabilities in here. And your job in that company is cranking that stuff out. So that's, I'm happy to talk with people. I've talked to some people in this line of work. It can be very demoralizing because you don't get to choose the target and it's just like given to you. So it may not be interesting, but somebody thinks it's important enough to pay for you to do that. So I don't know. All right, cool. Any ethics questions? Act ethically, please. All right. Oh, cool. Corporate bug finding. Great. We did this. All right. Awesome. Okay. So is working with defense contractors ethical? I will not touch that. That's, again, I think you need to make your own decisions about what is or is not ethical in your mind. Okay, so you've decided on a target. I would say one of the biggest flaws that I ran into, that some of you may also, is to resist the temptation to just dive right in and find bugs. Like, you've been doing pwn.college, you've been doing CTFs, you just want to like find bugs. You can do that, but and you'll find stuff, but it's much better to take time to plan it out, right? Like, how am I going to find these bugs? What tools am I going to use? Am I going to use static analysis? Am I going to use symbolic execution? Am I going to use fuzzing? I will tell you, if you can use fuzzing, use fuzzing. Fuzzing is absolutely, hands down, the best way to find bugs in anything. Like, you want to make money doing this stuff, the best thing you can do, find an important target that pays money, figure out what the important components are of that target that maybe pays you more. This is, again, kind of a metagaming thing. And then figure out how to fuzz that thing. Like, AFL++ is great. Use it. Fuzz stuff. It finds stuff. It's amazing. Yeah. Other things to think about. This is something that until it's bit you in the butt, you won't actually really think about, especially if you're doing static analysis or, the question is, why is fuzzing the best? Fuzzing is I have a lot of stories about this, but fuzzing is the best because it's, you get a result that is, if it's a reproducible crash, you get an input that causes a crash in the target. And that's like absolutely critical. Because then you can debug the root cause, figure out what's going on. And you can think of so when I was doing the XNU stuff, I was harnessing different things. And when I created it, which is basically like letting the fuzzer target that specific system. So I gave the fuzzer this one subsystem I was fuzzing. I think it was the PF, which is the packet filter, like before eBPF, like the E part, just the BPF. The firewall component, there's two different devices that you can talk to it from. It was like DevPF and DevPFM. And then where that went into the kernel code, it could select which one that came from. And I was harnessing it. I'm like, sure, whatever. I'll let the fuzzer decide which one. Thinking in my mind, like, this is stupid because how could that ever make a difference? Like, I don't even understand what these two different things are. I still don't understand what they are, but the fuzzer found a use after free bug by creating something on one and then deleting it on the other and then accessing it from the other one. And like, without giving it that thing, like, I never would have in 100 years thought that that could have possibly been a bug. Like, I grabbed the source code and I looked for these differences and I couldn't like see it right away. And so I was just like, yeah, whatever. I'd be like, let the fuzzer figure it out. So you think of the fuzzer as like smartly using a lot of input combinations to generate crazy inputs. So yeah, anyways, it's great. Okay, one thing especially, so we talked about Exchange, right? People configure systems, right? And oftentimes code is gated by that configuration. So if you spend 3 or 4 months finding a bug in Microsoft Exchange, and then by the end you say, oh crap, this is only a real bug if this configuration is activated, and it's a setting that nobody uses. I don't know, is that an important bug? Maybe, maybe not, but you probably wasted a lot of time. This is a really good thing for like doing pwn to own in these types of competitions, because you need to make sure that the stuff you're testing is the actual stuff that's going to be run. Okay, cool. Oh, we're flying by. Okay. All right. Very important to play the metagame. This is something I did not understand until the end of it, because I spent a lot of time just like looking for bugs and having fun, and it wasn't until the end I was like, oh, duh. Well, Apple pays more for bugs that are more impactful, right? So like, oh, I guess I should have said the $1 million thing. Obviously, I did not win $1 million, or maybe if I did, I wouldn't be here teaching you right now. I'd be relaxing and I don't know, retired and I guess living the good life. But they pay different levels depending on what the impact is, right? So just like we said, so on XNU on the Mac platform, there's a difference between root and kernel. So root does not have full permission to the system. So I think actually, like, I made the mistake where a lot of the stuff I was fuzzing and testing could only be done by the root user. which meant that the bugs that I found were root to kernel bugs, which are still bugs, and they paid, but not as much as if it was a user space, like from a regular user, or from even better, an iPhone app, from an iPhone app to the kernel and then a kernel bug. That would have paid way better. And I didn't think about that to the very end. And then I started, I actually have an example we'll go into here. But yeah, I didn't do that until the very end. And then by that point, I didn't have much time and I had to go back to school and everything. But by metagaming, part of this is like, what other bugs have people found in this target, right? So read write-ups. I know it sounds simple, but like there are people that write about and talk about these targets. What other bugs have they found? How did they find those bugs? Like, build on other people's tools if you can do it. Don't reinvent the wheel and build your own tools if you can. Like, if somebody's got a fuzzer for a target and it fuzzes component A, ask yourself, how can I just make it fuzz component B and then C and then D? And guess what? If nobody's done that before, you'll find bugs. Like, fuzzers shake out and find bugs all the time. Very important thing. What bugs pay the most? If you're going to spend the time on it, what bugs pay the most for your target? Right? Like, so for me, what I finally did was look at like, okay, what kernel drivers are there in the system, like in the dev/dev kernel devices, and then which ones of those are accessible from a normal user and not just root. And then I went in and started looking at that code and auditing that way. How much reversing is required? Do you guys love reversing? Are there any reverser heads here? Yeah? You should just leave. No, just kidding. But you have to think about that, right? It's like, do you want to be, because if you're finding a bug in a closed source kernel driver, you have to spend a ton of time reversing that kernel driver to understand how it works, what the data structures are, to even then start to find bugs, and then what to do with it. So think about that. This is actually, the ironic thing is I started because before I'd actually thought about targeting, I was just like, yeah, whatever. I like Apple products. As you can see, I have like already 3 on this table right here and 2 more in this bag, and 1 on my wrist. Is there any more? And I was like, yeah, it'd be fun to do. And I want to get better at reversing because I don't really like reversing, but I want to get better at reversing. And so I want to go through those kernel modules and do all this stuff. And then when I started looking at it, I found out actually the kernel is open source and the source code is there. And guess what? If I want to spend my time, I want to spend my time finding bugs, not reversing code. And I can read the kernel source code. It's amazing. And you can even compare it side by side in your editor and your IDA, so you can match it up directly and make reversing so much easier. Yeah, so think about that depending on what you want to do it. Okay. Leading to the next point. Why are you doing this? Right? You should understand your own, I know this, I don't know, this maybe sounds weird or metaphysical or something, but like, why do you want to do this and find bugs? This probably should have been the first slide, but do you just want to make money? Yeah, you can do it. You may want to have fun. You may want to learn. You may want to do a combination of those things. So yeah, what's your goal doing all this? How much time and effort do you have? Is this going to be just a weekend thing that you're doing while you're in school? So maybe you'll take 1 or 2 days a week, do some vulnerability analysis. If that is your plan, I would then use that to select a target correctly and make sure, because if you've ever tried to reverse something like 1 day a week, it can be a massive pain because you forget everything from your last reversing session. That stuff really like builds on each other. So if you don't have enough time, if it's something that's easier to reverse, or you can set up a fuzzer and just let it run and then check it once a week, that would be kind of a good strategy there. But you can think about your time and effort and how that impacts things. And again, what do you know? What is something that you know, right? What are your strengths? Play to your strengths. I've been saying fuzzing is great over and over again. Maybe you don't know anything about fuzzing. Maybe you're a code QL expert or a static analysis expert. Like, those are actually totally fine, but like, yeah, play to those things. Okay. How are we doing on time? How long does this class actually go to? Okay, wow. I guess I gotta go faster. Okay, let's do some ARM stuff. Okay. Anyways, selecting things. These are things that you should absolutely be thinking about all the time. Can you build it? Can you run it? Can you debug it? Can you modify it? Right? Oftentimes, well, I won't blow up anyone's secret information, but I know people that even though They had access to systems and access to debug things because they were able to build a complex target. They just added print statements and did print statement debugging. And for them, that was way easier than learning how to debug a target. But they had access that not many of us can have. And so you have to do things the hard way. So yeah, thinking about this kind of thing, this is like really important to figure out, because if you don't have a good setup here, you'll drive yourself crazy, and you'll know that you're not being as efficient as possible, and like wasted time is the worst time. Then you need to ask yourself, how can I attack this target, right? This is the key thing, and this is where like starting from a high level, right, and thinking about, okay, what are all the different ways that input gets into this system, right? And the better you think about this, you can think about things that other people aren't thinking about, right? So, you know, I was saying text messages on here, right? I think Android also had a problem. This was, I think, stage fright, where they would generate automatically thumbnails of any movie or image, but not maybe image, but anyways, I think the bug was in a audio or video library. Anyways, they were generating thumbnails even if you didn't even look at the text message of any message that was sent to you. And there was a bug in that image parsing library that allowed somebody to pop out, and so they could send you one text message and boom, your whole phone is compromised from there. So like thinking, like understanding that the system does that, right, is like a key part of understanding that attack surface. Where are things coming from? Where does the system get input? Where does input go in? Where does the output go, right? What things does this talk to? It sounds trivial, but in a complex system, it's like, it can get crazy. Other things, this is why part of the reason we talk about things at the lower division security levels, what's the access control model like? Who can do what, and what are the privilege levels? Modern systems are absolutely crazy in all the different privilege levels they have, right? A lot of things will pay out for privilege escalation, and it doesn't have to be a use after free that leads to a yada, 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 yada. It could be a logic bug that allowed you to do something you weren't supposed to do, and you can get paid by that stuff. Like a key thing that's absolutely crazy to me is, this is from research stuff, not bug bounties, but like WordPress. Anybody know WordPress? Is it an important piece of software? No?
Yes.
You all think PHP is like so boomer technology that, yeah, it's still like one of the most deployed and run pieces of software on earth. It's like insane. WordPress runs so many sites. And so you can have a cross-site scripting in like WordPress, and a lot of times you'll think it's, oh, it's just a self XSS, like it's an admin, and on the admin panel, it's a cross-site scripting. But it turns out in WordPress, there are super admins. Because you can have a WordPress install where you have a bunch of different separate WordPresses, and each of them are admins, so you could actually elevate up one more privilege level. And like, I didn't understand this until I was doing research with some people, and we found these self XSSs, and we're like, what actually is a self XSS? And you realize these permission models are just absolutely bonkers. So if you can understand that to the level that you can make it do something it's not supposed to do, then that's great and part of understanding the attack surface. Where's the data stored? How can you mess with data? What things you can change? Those are all basic kind of stuff. Okay, and what does the system depend on, right? The dependencies. Okay, another key thing, and I'm going to show an example here. This is the example I was talking about earlier. So you can spend, this is not a CTF. You need to get that into your heads when you are doing vulnerability analysis of a real target. It is not a CTF. Nobody planted a fun little vulnerability that you're just going to look at some code and find it immediately and be like, oh, this is great. I love this. This is like, there may not be any exploitable bugs. There may be plenty of bugs. They may not be exploitable. So you can spend a ton of time on one component and find nothing. And that's, or you can find bugs that aren't triggerable. This is like, yeah, this is crazy. I think a good strategy is to try to cast a wide net, as wide as you can. Look for easy, dumb vulnerabilities in a very shallow manner possible. See what you can find, and then explore those more. And then you can go deep as you get more experience in things. I think specifically the example here, I'll show you guys this. I think it was a similar, basically this is what I was mentioning. It wasn't until the end of my XNU journey that I realized I should be targeting important things that are in the kernel that user space a normal user could talk to. It turns out, anybody know SMB, Samba, what that is? Yeah, what is it? No, back there.
It's a way to remotely access files on another system.
Yeah, a way to remotely access files exported by one system to another. I think it's NFS, right, underneath, and this protocol is? That's a different one? Okay. Thank you, random person, who nobody in the room knows. So I started looking in that right at the end of my sabbatical, and yeah, so this is, don't get too excited. This is a version, so I was looking at I think, because I started this, I think I was looking at a version of XNU from like 2021, 2022. Anyways, at the start of my sabbatical, it was towards the end, like 9 months later, and I set the fuzzer up, I harnessed the SMB client, or the SMB stuff, and then it popped out bugs literally immediately. And they were the stupidest, like, copy the struct sent from the user has a length field that was never checked, and it's just copied right into kernel memory. And I was like, oh, I'm so smart, I am absolutely getting paid. Then I tried to run it, my POC on the test laptop that I had, couldn't trigger it. And then I realized that somebody had already found those bugs before I had ever looked at that. But in that time, like in the 6 months, like when I'd started my sabbatical, I think like 3 months before I started looking at it, they had already fixed those bugs. So anyways, I wanted to show this. I think it was something like this, of just like this put mem. So like put memory in here from this CP with this segment length, where the segment length was never checked, and just like copied in somewhere exactly like this. I wanted to find the exact thing, but I couldn't. I got a little distracted, but it was something like this. Anyways, so it's if I had just probably taken the time of understanding what are all the system calls that a user could access, and then just looking at them like 1 or 2 functions deep, like not even very deep, of like, okay, this user input, does it have a length field? Is the input weird in this struct? Let's look at where that's used. Let's look at where that's copied around. Oh crap, there's a bug. Like I could have found stuff like way, way, way faster than if I got like super deep into several things and tried a lot of stuff. So anyways, learn from my experience. Okay. Yeah, there we go. Final 2 things. So this is kind of a double-edged sword. I don't know, and maybe I'm just full of it, but we talked about reverse engineering. Remember, reverse engineering does not just mean understanding a binary, right? Reverse engineering is understanding a system. If that system is only in binary form, you need to understand that binary. So even if you have the source code, you need to understand the components and how they all work together. As you'll see, and later in the class, we'll get into like, I mean, we saw it there in that XNU code. You can like kind of see what's going on there, but it's not very clear. And there's these MBs, which are some buffers, and there's a special data structure that's only, I think it's used in network communication in the kernel. I'm not sure. I can't remember if that was a specific thing to that kernel module or not, but you have to understand things, but you have to remember this is not a CTF. In a CTF, oftentimes your reverse engineering goal is to understand every single bit and byte in that thing and to get this beautiful IDA decompilation where everything looks great because you know every single structure and every single field and everything. That is not the goal. There is no end state here. You could do that and not find anything. And then guess what? They'll release a new version in 3 months that completely changed the stuff and you'll have to redo it. And then 3 months later, things will change. This literally happened to me when I was trying to create an exploit from a POC I had, which was a heap underwrite. So it was writing a pointer like 1 byte beyond a thing. So I was trying to do all this heap grooming and everything to get exact thing that I could control. And anyways, I was almost doing it. I was very, very close. And then I upgraded to the next version, which was a point release. It was like 11.3 instead of 11.2. And they'd completely changed the way the allocator worked in the kernel. And they randomized it much more. And then my beautifully crafted heap manipulation was like completely dead. And I was like, I just need to submit this. I've spent like a month like trying to do this thing and driving myself crazy. But This is not to say you don't need to know things. I think that's the flip side of the coin. So I think one side of the coin is don't go too deep and too focused on things. You still need to remember that you're trying to eventually find stuff. Be cognizant of getting stuck when you're just spinning your wheels, right? And doing too much time reversing. But keep notes. I almost never take notes on anything. That was an absolute mistake when I started doing this stuff. Like having to reverse engineer what the bug is and why it works and why the POC works, or this allocator stuff, because I was, I don't know, traveling or doing something, but like I went like a week later to look at the thing and I was like, oh no, I like reversed 5 levels of this allocator and how it was working, and I had to do all of that again to re-understand what was going on because I didn't take any notes. And that's why I was like, okay, this time I'm writing a text, just whatever makes sense to you, the easiest, write in a text field, like just please take notes. Like this stuff is complex. It's not something you can always just keep in your head. Because this was the crazy thing, and this is a story I wanted to share, is that you never actually know when something is going to be useful. Like you may understand a feature and it may actually cause a bug to be triggerable that wasn't triggerable. So this was a bug I found to prepare for my wait, no, don't do that. Don't do that for sure. What are you doing? Okay. Anyways, okay. For my before my sabbatical, I wanted to like prepare and practice and get, I guess, limbered up or whatever. To do that, I tried to do pwn to own with somebody else targeting the Tesla. And so I did the exact mistake I was warning you against. I went super deep and I like found a feature that it's this feature where you can plug in a USB drive to get an audio thing to play, and the car doors open in sequence to that. I can't remember what the feature is called. And I was like, oh, this is a super cool vector. Like, think about just like plug the USB drive in and like, boom, you've popped the system. And I started digging in. I figured out the exact library they were using for this audio player, which was this GStreamer, which is an open source audio playing system. They also didn't do any checks that the MP3 file was actually MP3, so the attack surface was any of the installed plugins and libraries. So actually, I used Arbiter to found I think one potential bug that wasn't actually useful, but I did end up patching in here. So I used some static analysis tools, but honestly, it was a lot of reading code and just like I would grep through all this stuff for malloc or gmalloc, because it was actually a different allocator, but for gmalloc to find every single use and just like read the code a few lines back, and you can see super weird stuff like integer overflows, all this kind of stuff. Anyways, to, I guess, spoil it, I was never able to land this, and I drove myself crazy trying to land this because it was a, actually you can see here, so the vulnerability was an integer overflow here. So there's this MKV is Matroska, and this, basically there was this thing, so this block size. So if block size was very large, adding this constant value to it would cause it to be small. And so it would allocate a small buffer, and then later on it would copy block size from data to out data, right? A classic integer overflow. I believe, yeah, this is all in one function. So this like is very clear when you're looking at the code that this is a bug. And so you get super stoked. You're like, yes, I'm a genius. I found this bug. I'm going to get so much money. I'm going to win a Tesla. This is going to be awesome. Then this is not like hyperbole. This is like actually what I was stupidly thinking at the time. Anyways, and then you create this MKV file. So you find out the MKV format. You create an MKV file that does exactly this thing. And then you do it and it doesn't work. And you're like, why doesn't it work? This is insane. There's a classic integer overflow right here. Well, you realize that actually there's a size check. So there's a size check in this other function. So again, this is why this stuff can be very complex, especially with static analysis. You can look at one function or several functions, see that there's a bug, but not realize that's 15 functions deep, or that data that you're using was checked in an earlier part of the code you haven't even looked at for size or something like that. So there's a size check, which checks max block size, which I believe was, I don't know. I can't remember the size. I think it was 15 megs or something, which is not enough because I guess I don't have it here. But this block size, I think was an int, so a 32-bit number. I think that's right, because it was like a 4 gig overwrite. Yeah, that's the only thing that makes sense. Anyways, so so to do this, because this was a fixed thing, you would have had to create a block size that was almost 4 gigs, right? And then added a little bit more that would create a small buffer that you could overwrite with your huge buffer. But this max block size stopped that. So it only allowed your block size to be 15 megs. And so I was super disappointed. And then like a day or two later, it dawned on me while I was reading this code that there was a feature in these blocks that had compression, so that you could decompress the block size. And that happened after the size check, but before this copy. And so what I was able to do was, it was zlib, and there was 3 different compression mechanisms. I had to test all of them to see which one would actually let you create a resulting file that was the size I needed of 4 gigs in memory. And it was actually able to do that. So using those 2, like using the knowledge I had learned just from reading the code and kind of doing that reverse engineering process, was like, I would not have been able to trigger that bug without this thing. So anyways, but landing this was almost insane. Like doing, I still have like nightmares of trying to do this, because you have, it's an audio file, so you have 1 shot, right? And so I arranged the heap so I could survive the 4 gig write by making other tracks and everything that get allocated and massaging the heap. You could survive that 4 gig write, and then you're like, great, I did that. What do I write? Right? Then you start looking, what are all the structs I can allocate? Great, there's a function pointer. But there's ASLR, so I can't just arbitrarily do anything. What are the targets I can go to? And I like tried a bunch of things, couldn't find anything, and I had to like stop, because I was like doing this on weekends and like hating my life on those weekends, because I was just getting stuck on this, because I'd gone down so far in this rabbit hole of like, this was the only way I was going to do this, and it was just like horrible. So anyways, learn from that. Okay, questions? Okay. Do you guys think you can hack stuff now? That's mean. Not here to defend himself. What's going on? Okay. Well, let's see how late you are. We'll do like 20 minutes of this. Okay. Source. Where was that stupid thing? Exploit me? Okay. So now we are in. Oh, and then the silly thing was, so I spent all this effort on this this stuff, and I thankfully had read that Google has a vulnerability patch program, where they will pay you for patching vulnerabilities that exist in important open source software, and what they define as open source is anything that's been harnessed with OSS fuzz. And this stuff was harnessed with OSS fuzz, so I was actually able to I got like $500 from this. So at least I got something out of like 3 months of effort, besides purely failure. But and it was cool. I got like a bunch of bugs fixed, so that part was fun. But yeah, it was crazy. Okay. Here's our program. Have you guys ever group hacked before? So we have this program, exploit64. There's level 1 is hello as the password, hello and pass in a value. Value less or equals 0 is not allowed. So what do we do next? Obj dump. And I can just use objdump because this is actually the one nice thing about using an Apple Silicon Mac is because it's running ARM with UTM or whatever that I'm using, and Apple's virtualization stuff. I can run a native Linux VM locally on my thing, and then all the tools work when it works, and so that part's kind of nice. But okay. Oh God, it's Oh no, does this mean it's whatchamacallit?
Yes.
Yeah, it's C++. I'm regretting this immediately. Okay. Also, we just crashed object dump. Is that a failure? I feel like that shouldn't happen in object dump. Oh, good. Okay, see, it's so resilient. Okay, let's grep for level 1. Okay, then we just open it up in IDA because we tried this and said, yep. Okay.
Oh, 13.
13?
I thought 13.
Oh, level 13. Yeah, so this is a multi-level binary challenge in one binary, basically. So it's I don't know. I just saw it on GitHub. I have the link somewhere in here. So if you want to try it out, you can. All right. Source. Exploit me. I know you all saw that source directory, but we're not going to do it. All right. Should we start at the start? At main? Can you all read this? Or do you need me to zoom in somehow? Back row? Yeah? Okay. Oh, somebody said, why do I look like Tom Cruise? Well, I don't know. All right. Okay. Printf puts password hello. If strcomp rv1 passwords. Looks like we have all the passwords here. Hello, help, velvet, my secret. Pretty nice. We've already got passwords. But we actually want to exploit it, right? We're not just here for the free passwords. Okay. Okay. So this is, okay, so argv1, I gotta assume, oh, sorry. Oh, this is passwords, a help. Oh, I see. Okay. It's supposed to be a list, and then it's like hard coding the value there. Passwords, argc, get effective user ID. Oh, a nice function called int overflow. That seems helpful. Okay, so argv2, so our second argument. So our first argument has to be the password. The second argument is there. Int overflow. Okay, so what's it doing? Taking our input, atoi, turning it into a local int. Value less than or equals 0 is not allowed. If word, okay, so now it's if not it. What was that? Yeah, okay, let's, oh, the word. I hate these stupid things. Okay, let's go here. Well, let's, now I want to give names. Int. Okay, great, okay. I see. Yeah, okay, I want to look at the assembly. So this is a, okay, so we can kind of clearly see by looking at this. So move, wait, store register, load register, store register. What's var8? Why didn't this update? No. Okay, bunch of redundant stuff. Compare W0 with 0, and then store H. We looked at that last week, right? The yeah. So this is the, okay. So it's still a 30. Okay. So it's reading in a 32-bit, right, which is the W0s, and then the H here means what? Half word, just 2 bytes. Cool. So what number do we need? Yeah, so OX. Actually, the thing I really like to do, there's this really handy dandy bit thing here of like doing like that. So you can just immediately set the bits. I mean, 10,000. Come on. I can't even say it's off by 10 because that's.
Can you input hex into HI? I can't remember if it actually.
Exactly. So that's the other. See, people are already thinking through. So the other question, right? So we think we know the bug. The bug is that this check is a 32-bit integer check, but this check is a 16 2-byte. Wait, did I say 32? Yeah, 32 and 16-bit. So if we can pass in, and this happens all the time, and it's very helpful if you have like a multiply that causes an integer overflow. You need to make sure that those two numbers that you're giving are in the right proper thing. So making sure that it's right within that range of like larger than this but smaller than this. So 10,000 hex, and yeah. So we'll just do a quick man, because especially in honor of Rob, since he's here, we'll read the man page of ATOI hex. We will search through the man page. Ah, there we go. No, because the behavior is the same as string to long, null pointer 10. So string to long is where you can specify the base. So now our theory that we have developed as a group, what was it? Hello. We pass in hello, and we pass in 65536. Oh, look at that. Whole bunch of hackers. How many people is in this room? Like 20 something? Look at that. Okay. Help. I need somebody. This is actually kind of fun. I don't know if you're having fun, but I guess the question is, do I care? Okay. Attack overflow. Do we want to try to overflow things? Like overflowing things? Okay. Username and password. Okay. Username, password. If verify user, username is not equal to 1, return 0. Okay, so there's some check. It's going to check the input of username. And again, this is where I like to not go too deep and like be like, oh yeah, well, what's that function? And what's that function? And verify user costs something else. It's like you can just look at it as like, okay, there's some check, obviously, because there's some if condition here. Copy onto v4 funny, then copy onto the second argument password onto v5. And then, should this be a character pointer?
Could you name the keys that you hit for these main shortcuts?
Oh, is this like what you get asked in class and now you're reflecting it back on me? Yeah. It's like asking me what Emacs shortcuts I do to do things. It's like built into my brain, but yes, I can. Okay. So let's see. N is to change variable names. So you hit N, you can change the variable name. Hit Y, and you can change the type. The thing that will drive me crazy is why people develop tools where you can change the type that has the name in it, but if you change this name, nothing happens. It's the most insane thing that anyone's ever developed, a system that shows you this. There should be one thing. You can change the type and the name, and it should just change. Anyways, okay. And then I think the only other ones I've been using are, let's see, function F5 to make it try to re-decompile. Tab is the really important one to switch easily between decompilation view here and then the so like clicking on verify user, this means when I press tab it should be synced with that code here, and so I should see a BL Z11 verify user PC. Oh, it does demangle it. That's kind of cool. Is this a new thing? It always did it?
Like since IDA 7 or something.
Oh, okay. The free one. Okay, funny over here. And then the other one is escape. So escape goes backwards. I don't know how to go forwards. Is there a way for it? There must be, right?
Can you go forwards in time?
Can you not go forward? What? Are you defending IDA?
If you press escape and then look in, like, there's two arrows, and if you hover over them, there should be...
Jump to next position. Or, yeah. Jump to next position. Oh, wait. Yeah, but what's the keyboard shortcut? Anyways. Okay, so copy v4 funny v4 password, some string length. Why is it string length 0? Is that like C++ stuff? String length on v0. What is this doing? Probably checking the end of the string or something.
No,
this must be a buffer, right? This is clearly a type. Yeah.
Same thing is funny, so it's forcefully making it the same string size.
Right. Okay. And then the other thing that's but why?
No, it's the regular. It's either the regular string length or it's like
okay. First, other thing we can do is the string comp, right? So we have string comp v4, v5. String comp always takes 2 character pointers, so it's passing in the address of v5, which means v5 must be a buffer, right? It's not so the type here is wrong. It's saying that it's a 64-bit, so it's what 64-bit would be character, 8 bytes. Is that right? Yeah. So that makes that look better. It makes this look worse, which is weird, but okay. Oh, see, and then, yeah, this is how you can tell that your decompilation is getting, your reversing is better as the decompilation gets better. So doing this, so calling stir length on v4, so however many characters v4 is, it's then nulling that byte of v5. Is that right? So the string length is 2, yeah, 0, 1, 2, so that way the resulting string is going to be the same length. Cool. Okay. And then if v4 is not funny, then so the password, the idea is checking that it's funny. Why doesn't funny work? Should just pass in funny and it work? Oh, login selected, but you still failed. Wait, login failed.
What if you want to verify user?
Let's go to verify user.
What's in there?
Okay, pressing N for username. Stop doing dictation. Okay, username. So similar thing, there's a v2. Copy admin onto there. Well, this is like the same thing. If only we had a way to like detect macros and common inline functions. On v3, so I will go ahead and press Y to call this a ca. Buffer size 8. Return 1 if it's not comparable to admin, and then login failed. But where do you get the flag? Oh, yeah, that's funny. So there's this nice function called stack overflow, which should have been a hint. I don't know why I wasn't thinking about that, but cool. Okay. All right, should we overflow this? Yeah, maybe? No, you don't want to? Okay. So we're stir copying into v3 here, the username. I guess we can technically choose whichever one we want. So let's help. Let's see. So admin funny. Login succeeded, but we still failed. Okay, so we do know the stuff that it wanted. So if we did a bunch of A's, I think this is, you should all know this. Bus error, core dumped, awesome. Okay, so we exploited it. Now what do we want to do? Or we haven't exploited it. We've proved that there's likely a vulnerability because we caused some weird stack behavior here. Wait, somebody says they didn't know tab syncs it. Oh man, okay, I guess Rob was right. I hate it when Rob's right. Okay. So we are copying into, this is where I don't trust IDA, but okay, this is our string copy. So if we're using string copy, what does that mean? What was it? Yeah, it doesn't, like, implicitly checks. It means our payload can't have any null bytes, which is a massive pain. Right, so this is always, I think, Home College can do a lot of, especially even in the challenges we're giving, a lot of hand-holding by using the read function, which accepts any number of bytes. And so it's really important on a real target to understand and take that next step and be like, okay, but how is it reading in and what constraints is there, right? Is it a scanf, which means no spaces and new lines and other things? Is it stir copy of how it's getting passed around, which means Stir copy will keep copying up to a null byte, which is going to be a pain for you. So yeah, this is definitely something to remember here. So then where are we going? Yeah. So, okay, so then what we're looking for is something like a win function. That's our next intuition here. So the way I would look, there's a nice handy dandy sub view. I almost always run strings on the binaries, so it'd be hard here because there's like 15 different levels in here, but strings would at least tell us all the strings, so we can look for like flag. Well, we actually need the next level's password.
So probably want level 2 passwords.
Yeah, we want level 2 password.
Or you know where that password's
We do.
I think you already saw that video with the main function. When it was checking all the passwords different.
There it is.
Where?
Scroll back up. I think it's like OX1, 2 in the left.
Oh, perfect. Okay, level 2 password. Where is it? So? Okay, yeah, great. So I double. I'm like terrible at IDIS. This is very weird to people think that I'm actually good at this. Okay. Okay, so level 2 password, we found out where it prints it. Awesome. We double click that. That takes us to, now we're in the pseudocode view. We're in read-only data, so this is data that's in the binary at this address. I didn't do checksec on it, but I assume that this is going to be non-PIE, so these will be at fixed locations. And then level 2 password. So then I'm going to hit the X button to do cross references. So this shows you what other parts of the code that this is analyzed that reference this specific thing. You have to be very careful. This is not the ground truth. This only does like a direct reference. So when the code like says, hey, load that address there. But if it's part of like an array, if you xref like the third or fourth array element, but it only accesses it over an iterator, it will not, like the decompiler can't know that it actually accesses it. So this is only like direct access. So you do have to remember that. Okay. So now I double clicked on that. That takes us now to the IDA view of where we are in here. And then I'm going to hit tab to decompile it. We want the level 3 password. All right. Okay, well, we have level 1 password, level 2, maybe. So I hit slash to then search. You can see the slash at the bottom. And I'm gonna type in level. No.
What if I blew your mind by telling you you can do Control F?
That was gonna be my next one. I think slash though does like,
like
incremental search, just like in less. Yeah, there we go. Okay. Level. We want the level. Wait, what is this? Level 2 not synchronize? Level 3 password. There we go. Boom. So we do have our target. Okay, great. So we have our target is level 3 password. Oh no, I don't have it set up. Usually, well, I guess I go back and forth on if I have the addresses on here, but you can see the addresses here. It's 401178. So we want to overwrite. And okay, so we have our target here. Okay, this is where I should start. Okay, this is where I'm just going to take notes here. Let's do 401178. Okay. 40. Well, we already know the password, but this is cheating. Don't look at the password. Okay, 401178, and now we need to go back. So I'm going to hit. This is the other thing I really don't like about IDA is like the IDA view and the pseudocode view. The backs are different, and so what I mentally wanted to do was to go back to that original decompilation view that we were looking at of the level 2 of the Stack Overflow function. But if I kept pressing back here, I don't know that I would get to that because it's a different backwards and forwards thing. This is why your brain gets melted by the tools that you use. Like nobody should think about that. You should just be able to go back and forward, just like a web browser. Anyways, okay. Nope, that was the wrong one. That will let us down. Okay, Stack Overflow. Great. Okay, and so we're in verify user. So now let's look at the binary code. So okay, the way this is working is. So 30, if I remember correctly, when it does var underscore 30, this means 30 hex. Is that right? So store pointer 29 and 30 at the stack pointer, first decrement, or for increment the stack? That doesn't make sense. It should be decrement, right? So it should be minus 30?
Yeah, all the bars are minus.
I actually find IDA very poor. Like, I actually like object dump, but yes, okay. So minus 30 hex is, I think if you double click this, it will show you, oh yeah, wait. Bar 30. Yeah, so this is minus, this actually does mean minus right on the left. This is the view of the stack layout. When you double click on a variable in the disassembly view, takes you to this. And then if I escape does bring me back here. So, okay, so decrement the stack pointer by 30 hex and then copy at that location 29 at 30, 30 there. Set this all up and then, yeah, load pointer, again, exactly the same thing. Stack pointer plus 30 minus 30. Okay, so we should be able to. Okay, I want to do this in a very silly way. I don't want to do like a whole Pwn Tools thing. You guys will be okay if I just do really crappy code, right?
What is that different from Pwn?
The difference is if you choose to do it. Okay. Oh no, there's going to be a pain because of the bytes, isn't it? God, I hate Python. Why do people do this? Fine. Okay. I refuse. Okay. Okay. Echo B, E. Okay. We want, so our buffer is, if we look at this, okay. So now we need to know where our buffer is. Our buffer is on V3 and V. Okay, so this is the first stir copy is admin. We want the second. Wait, where's the other stir copy? Oh, is this an? It's a like inline stir copy because it's a constant value. Oof. Okay, don't want to reverse that. Ignore. Oh, you can see the admin and then the n. It has to get the n in there. That's what this one is. Yeah, because it's doing 4 bytes. It's doing the ADMIN and then the N. Okay, so stir copy, the first argument is the destination, right? Stack pointer. Look, I hate this. Okay. So stack. So this is 8. Let's do. How many A's do we all think we need? 20? 28?
And then another 8 figure same register.
Yeah. So I like to do that plus B. So I just like to, I don't know. You can use, I'm sure you all are very good using cyclical and doing all that to find out that stuff. I don't know. That's all newfangled stuff. For me, I like a good old fashioned just print out the stuff. Bus error. Okay, great. We can GDB. And again, I can do this because this is an ARM system. You will not have that that use. Incorrect. These are A's, not B's.
That's embarrassing.
Yeah. Hire good people. Okay. probably the point where we should debug this, but. Just randomly trying stuff in front of people is good. Oh no, we're almost done.
It's actually just 8.
Hmm?
I think it's 8. 8 A's and 8 B's.
Oh, duh, because there's 2 8-byte buffers. So it wasn't 8, it was 16. Okay.
Well, you win some, you lose some.
Well, yep, okay. So great, now we got there, and now let's see, where do we want to go? We want to go /x. I put it here, 78, 11, 40. I shouldn't probably have to change the 40. I'm just gonna do this.
Yeah, you probably want echo EM.
Look at that. And why are we looping forever? Exactly. So let's do what's 8 plus C? Oh, I did that. Can you believe that? I did hex plus 4. All right. So look at that. We did that. You guys all did it. You can do it on the homework. It'll open in 50 minutes. So good luck.